We will admit the last ones here, yeah?
Yes.
Then I think we can start.
Perfect. So welcome everyone to this webinar with the title of Design Forecasting, a Designer's Perspective. Good morning, my name is Ehsan Qasem. I'm Associate Professor at Jönköping University, and together with my colleagues, we run this webinar. This is the second webinar in the module 7 of WebLearn. We are running a series of webinars related to metal and polymer component manufacturing. You could go to the next slide, please, Jakob. The list of participants you see on the slide, we are very happy to have many of you today from different countries. It's a very international webinar, as usual we have in our WebLearn project. Welcome all of you to the webinar. Next slide, please. So WebLearn is a project that is supported by Knowledge Foundation as a funding agency in Sweden. It will run for at least 2 years. And in this project, we focus on the topic of metal and polymer component manufacturing. And every 2 weeks, we have one webinar related to these topics. It covers the spectrum of topics from simulation and modeling, theoretical topics, as well as experimental and manufacturing aspects of components. What we try to do in our webinars is to have a mixture of theory and practice in order to make sure that the webinars are useful for practical applications in industry. In addition, what is unique in our webinars, we try to have a good engagement from the participants into the webinar to make sure that it's not only one-way knowledge sharing, but also we see it as a platform for sharing ideas and also networking. Next slide, please. Today, the moderators of the webinar is myself and my colleague Madeleine Zetterlin, who will join soon, and we will take care of the technicalities for the webinar. Next slide, please. But most importantly, we have the lecturers for the webinar today, as you see on the slide, Jakob Olofsson from Department of Materials and Manufacturing, School of Engineering, Jönköping University, and we have Giacomo Bertuzzi from Italy as SQE manager at Petrol Valves in Italy. We will be honored to hear your slides and presentation about the topic. Next slide, please. This is the brief agenda of the webinar today. We will start with the presentations very soon. After that, there will be a panel discussion after almost 1 hour presentation, where we discuss the topics together with the lecturers and guest lecturers in the webinar, and you're more than welcome to participate and attend with your questions in the panel discussion and contribution. We hope to wrap up the webinar before 11:30 Swedish time. Next slide, please. So a little bit about the format of the webinar. It would be appreciated if you could turn off your microphone during the webinar. Questions are more than welcome, but we appreciate if you raise the questions in chat during the presentation. We will answer the questions at the end of the webinar or as the lecturers will prefer. There will be a panel discussion that, as I mentioned, is a very important part of our webinars where we try to have engagement from the participants as well. So feel free to contribute with your ideas, your opinion, and also if you have questions during panel discussion. Our webinars are recorded. We will make the recorded videos available to those who have registered for the webinar afterwards. So if you do not want to be recorded in our webinars, please, your picture, please turn off your camera during the presentations. But when we have the discussion and panel discussion, we still record those parts as well, but we will not share the panel discussion recorded video in case you want to discuss deeper topics. So feel free to turn on your camera during the panel discussion in case you want to discuss something or you have any questions. Next slide, please. For those who are not available with Zoom, this is the interface in the Zoom. On the left bottom part, you see the buttons that you can use for muting and unmuting your microphone, turning on and off your camera. And also in the middle, you can see the chat function where you can use to send the questions either to me, Ehsan Ghasemali, or my colleague, Madeline Zetterlin, or send it to everyone. And as I mentioned, we will take care of questions after the presentations. Next slide, please. That was from me. We are looking forward to hearing your very interesting presentations, Jakub, and the guest lecturers from Italy. So, Jakub, the scene is yours, please.
Thank you, Ehsan, for this introduction, and welcome again, all of you, to this webinar. As you see, the topic for today is design for casting from a designer's perspective. As you might, some of you were also in the first webinar in this series where we looked at design for casting from a foundry man's perspective. So then we took the foundry perspective on geometry and designing the part. And today we're going to look at it from a bit of a different perspective. So what we have today we have with us here Giacomo Bertuzzi from Italy, who is has been working as a design engineer working with casting, and we're going to share with you an example on how to design and taking the manufacturing process, the casting in this case, into consideration. I met with Giacomo some years ago. I think it was an Magma user meeting. First time we met in person, and then we were working on similar topics and had this collaboration. And we're going to share more about this today. During the presentation, we will also have some breakpoints where we will have the possibility for you to ask questions for clarifications of the presentation, because we're going to do the presentation in different stages, and then you have the possibility to ask if there's something that you're not following. So if you have some questions during the presentation, wait until the breakpoint, and then you can ask the just for clarification. And then in the end, we will also have, as mentioned before, a panel discussion where we'll talk more about this concept and discuss and be open for questions. Yeah. So before I hand over to Giacomo, I would just like to briefly introduce myself. I know some of you from before, but those of you who haven't met me, my name is Jakob Olofsson. I'm grown up here in the southern part of Sweden, where there's a lot of trees. So when I grew up, I wanted to work in the forest and drive these cool machines that we all know about. And I was really interested in how these, not only how they could operate, but also how they could actually take these kind of large loads and really handle all these trees. And at school, I had a teacher that got me really interested in this technology that makes this possible. So I didn't become a driver of these machines. Instead, I went to the university and learned about how to do this development and learn about materials and finite elements, eliminations, etc. And so my first real job was actually as a design engineer of industrial gas turbines, working with development and design of this. I was a design engineer, and there it's kind of crucial that you also understand the material behavior. So I got really interested in this, and I also worked for some years in the automotive industry, working with multi-body dynamic simulations, finite element simulations, topology optimization, etc. Before I went back to the university, to academia, and did my PhD on how to connect casting simulation and finite element simulations, and taking the manufacturing process into consideration when designing, and working with what we call local properties, where you actually take the local microstructure and defects, etc., into account. And I'm still working in this field 12 years later, since I started at the university. On the more personal side, I like to go camping with my family, for example. I also play a lot of music, and but that's enough about me. And I would like to hand over to our guest, Giacomo, and let you introduce yourself a bit to the audience. So I will stop sharing here, Giacomo, and then you can take over from here.
Okay, thanks, Jakob, for the introduction. Okay, before starting, I would like to thank Jakob for the opportunity of sharing some work that we did together a couple of years ago. And before starting, I'd also would like to thank people that are not here today because they are a little busy in other stuff. Matteo Cova and Riccardo Cenni, two of my former colleagues that supported this project, and Scarpa Gianpietro from Enginesoft in Italy that supported the project from the simulation point of view on casting technology. But time is running, so we can go ahead with the presentation. First of all, the summary, I will just introduce a little bit myself more in detail. Then we will go to the first step, that is the casting component design process. We will go more in detail on the design side and the foundry side, and then we will also introduce the idea that we call the fully coupled optimization. Then we will see an example of the methodology application, mainly starting from the easiest way, that is just the structural optimization of a CAD component. Then the step 2 will be the structural optimization considering local properties. That is exactly the field where Jakob is working so far. And then at the end, we will see what we call it half-couple optimization. So a sort of optimization of the casting process and the structural optimization. And then, of course, there will be conclusion. So let's start with myself. I'm Giacomo Bertuzzi. I live in Italy, close to Bologna, so north part of Italy. I took my master's degree mechanical engineer and my PhD in mechanics of materials at the University of Bologna. During the PhD, I worked mainly on the field of aluminum foam. Then since 2008, I worked in the industry, mainly related to foundry business, both as a casting end user and directly in the foundry. Meaning that I've seen both the two sides of this field. At the beginning, I started as a designer of casting components, supporting also people designing casting components, giving also feedback from the manufacturing process. And then I worked directly in the foundry business as a in the casting technology department, so mainly in the technical department and in the quality department. My background is more related to the car iron casting, where I worked both on manual and automatic forming, but I have some experience also in steel casting and aluminum casting. Nowadays, I'm working in Petrovalves SPA, is a company located in Castellanza, between Milan and Varese.
Seems we have a technical problem here.
Castings, but we work also on other field like machining, forging, welding, and so on. So let's start the presentation. When we speak about the casting component design process, usually we start with the design of the component. So the design has some tasks, has some requirements, mainly related to functional and structural design and project or component reliability. And he has to develop a shape that fit the requirement. And to do that, usually is supported by some tools like the CAD file for the shape and geometry definition, the stress or reliability analysis with the FEA model to evaluate if the stress on the component fit the strength of the component. And he can also use structural optimization, as Jacob mentioned it, like topology optimization, where the material is put where needed, or shape optimization, where we change the shape of the components to get less stress, and also the geometrical optimization, for instance, when you optimize a radius or something like this. So at the end of the design, the shape is sent to the people that are in charge of developing the technology to produce the castings. And the task of these people is to get components that are sound, meaning that no indication on some area. They can also improve locally the quality of the material driven by the designer. And of course, they have to be in control of a process that should be robust. To perform these activities, usually the foundry can have some help from the pattern definition using the CAD file. Of course, they can also, with the CAD, having a casting process layout, so meaning that they have to study the gating system, the feeder and rising system, and also the chillers and so on. And they can be supported on making the right choice by casting process simulation. Usually what happens is that the design transfer the information to the foundry. So it gives information about the influence of the distribution of the mechanical properties according to the stress analysis, and also the influence on the component quality acceptability, meaning that it should be defined where the component is acceptable, which kind of defects are acceptable or not. But we need to understand that the best way of developing a casting component is using a co-design. So there should be a dialogue back and forth between the designer and the technology, and in that case, the manufacturing technology, just to get the optimum from the manufacturing process. And so we can say that the shape optimization of casting components should consider technological aspect. No wait about, no. This is something that is almost done by everybody, but it's better to focus on that part. If we go more in detail about the step of the project, we can see that the project started with the requirement that can be related to performance, manufacturing, functional of the components, quality, assembly, and so on. And the project should get out outputs like safety factor, weight reduction, cost reduction, and whatever you want. So the first thing that the designer does is to define a geometry and to work on the geometry with the structural analysis. So he knows the load, he knows where the deformation that are acceptable, and start to design a shape on this to reach the requirement. As you can see here, there is two round with an arrow, meaning that these are points where an optimization can be efficiently introduced. Then, as we mentioned before, the design of the component, the geometry of the component, and the requirements about the effects, acceptance level, or stressed area, and so on, is shared with the foundry that develop the foundry process. So what is made is that they perform the pattern analysis, considering the parting line, the cores, and so on. But also they work on the process, defining the chemistry, the feeding system, the gating system, and the chills, and so on. So far, the casting simulation can offer good tool to optimize both the chemistry, the feeding system, the gating system, and the chills. Then at the end of the simulation, let me say, or the technology development of the casting, what the foundry, the output of the foundry are the defect, or better, an idea where they could be located, the microstructure, and also the mechanical properties, because there is a strict link between microstructure and mechanical properties, and the residual stress. This information can be used both to review the structural analysis, to be sure that the stress that we get is aligned with the strength that we can get, and also to introduce, for instance, residual stress in the structural analysis to redo the structural analysis. And also all the data from design and foundry process can be put in a post-processing where the local stress is compared to the local strength, just to get the output of the safety factor, the weight, and the cost. So this is briefly an introduction of the project, more in detail of the project of a CAD component. When we started looking at this process more in detail from the designer perspective, that we went to that idea of the full coupler optimization loop. You know that there are a lot of optimization algorithms, and they need some driver. So some variable that drive the optimization loop, and then we go to convergence with the output that we require. So the idea was that the driver of the full couple optimization was both the driver of the casting simulation, so the geometry that can change, but also the variables of the process, like chillers, feeders, chemistry, and so on, and coupled with the driver of the structural analysis that can be the design, the shape, and so on. And of course, the output that drive the convergence, so the feasibility of the optimization process, should be both related to the structural optimization, so meaning the safety factor, the weight reduction, and so on, but also related to the casting design, just to get a robust and cheap casting process. So we start with the geometry, we perform a casting simulation, and we map the local properties to the machined part. So we make a sort of virtual machining. Then this is put inside the stress analysis to get the output. If the optimization loop is converged, then we are at the end of the optimization. Otherwise, we will perform another loop, and so on. Of course, there are pros and cons on this method. That first of all is that the variables that rules the entire optimization are both the one of the foundry and the one of the structural optimization. But we need also to be aware that sometimes the output of the both of the two optimization are not aligned, meaning that it's not easy to get convergence on these kind of activities, and this was something that stopped us that point. There are some practical difficulties in the optimization loop due mainly to the fact that there are a lot of software involved, and it's not easy sometimes to get them speak together. In that loop, you should have, for instance, a CAD software, casting simulation software, FEA software, for sure some Excel file to post-process, and at least the software to perform the optimization. So minimum, there are 5 software involved in this kind of activities. And you can understand that it's not easy sometimes to get them communicate each other. First breakpoint.
So we reached the first breakpoint, and if you have some questions, just you can raise your hand. I have a short question, or maybe I think it will come up when we go into the panel discussion. But when you showed the slide before, where it's kind of an iteration. You're moving information between. Yeah, at this point you can look. You see that already here you have the traditional borders, sort of say, between design and the technology foundry process. And the interesting thing with these arrows is that you're kind of crossing these borders. I know that now both you and I are maybe kind of special cases where we have both worked as designers and also in the materials. But what do you think typically is the problem with moving between borders here?
First of all, Jacob, I think my experience told me that the first big issue is that usually design and foundry, designer and foundries don't speak the same language. So the first is the alignment on the language. And the second one is that sometimes the sharing from the designer's perspective is a little bit tricky, because it is considered their own knowledge. But to break these limits, it's important to sharing all the stuff and be really open to get feedback from the foundry, to give more and more information. That's the main. I think that if you speak the same language and you are really open and sharing all the information, then these 80% of the work is done. Then there are technicalities. This is the first thing. The second thing is that it's important to involve the foundry from the early beginning of the design process, because sometimes what's happened is that you get the design at the late stage of the design process. It's not easy to change to change the geometry to fit the request of the foundry. So the foundry is forced, the manufacturing is forced just to follow the shape and not to get the optimized solution.
Yeah, thank you. Let's see if there are some other questions so far. I don't see any raised hands or questions in the chat, so I think we can proceed with the next section here.
Okay. So we did an example of this kind of interaction with the cast part. It was a ductile iron castings, 5 tons. Here you can see on top the cast part with the allowances in blue, and then the machined part with the machined surfaces in green. So we performed, as we mentioned, 3 steps. The first one was just the structural optimization with uniform mechanical properties. Both stress strain, the relationship was homogeneous in all the cast part, and the strength was considered homogeneous in all the cast part. Then the second step was the structural optimization, but introducing local mechanical properties, both stress-strain relationship and the strength. And then the third one was the half-couple optimization, where we started from the casting optimization, casting technology optimization. Then we moved the result to the structural optimization, trying to connect more and more these two fields. From the structural point of view, we could, these are the variable that we could change. So we could change the central cylinder diameter, its height, the thickness of the external ribs, the thickness of the base plate, the thickness of the central ribs, and the thickness of the lateral ribs. Here we see an
Just
example.
Just a question before you proceed, Giacomo. Can you
Yes.
give us some indication of what kind of size of this part we are talking about? Is it a small part or is it?
No, it's a big part. It's around 5 tons, and consider that is 1.5 meter times 800 millimeters with height around about of 500 millimeters. So it's quite tough. It's made for hand molding.
Yeah, so it's quite a large part. This.
Yeah, it's 5,000 kilos or 5 tons, more or less. Here we can see how during the optimization, the algorithm that is behind optimization could change the shape of different variables that we have seen before. Of course, driven by the result that he got. And you can see that we have some finer mesh where the more stressed area are located. So here you can see we use the N6 and Excel to map the load and to drive the change on the geometry. At that time, we used SolidWorks as a parametric CAD file to change the geometry. Then there was some constraint on the holes and on some area, and of course the load applied. Here you can see that the design variables could change from its medium, from the minimum and the maximum. So they are not fully free to change, but we have some constraint on changing. For the central cylinder diameter, central ribs, and diagonal ribs, we use a change factor that was just multiplying the starting dimension, while for the other we get we used a specific limitation on the change. And the output variable was related to 3 different zones, the more stressed zone, where we ask for zone 1, zone 2, and zone 3, different kind of max stress, max principal stress. So in some area, max and minimum stress. And for all the components, we asked to get a safety factor more than 1.3. So we performed our structural optimization using just uniform material, meaning that the strength of the material was uniform all over. And we get, for the first optimization, the safety factor 1.3 and a weight of 5 tons or 5,000 kilos. So we considered that the target was reached to get the safety factor 1.3 and all the process variables, process outputs were below our request. But it's well known that the casting components is not homogeneous and the properties can change locally due to the casting process itself, due to the geometry, but also to the casting process itself. So we approached the work of Jacob, the closed chain of simulation for cast components, and we used the information inside to add some local properties based on casting simulation. So we changed locally the stress strain curve, applying the Ludwigson criteria. So from the casting simulation, we mapped this kind of laws that correlate the stress to the strain, and we mapped these on the component before the stress analysis. Here you can see different material used in the stress analysis, and here the results using both homogeneous material from the stress strain point of view and material, dedicated material for stress and strain. In that case, we agreed not to change the stress strain curve because for the first running, you have seen that there is not a big difference because the it looks like it was related to the thickness, the big thickness of this area. So the influence of the change on stress strain rules were not, we could not appreciate it. So we decided not to use this, but it doesn't mean that, for instance, for smaller components, as Jacob demonstrated in his work, you should use also this kind of relation. What was quite relevant for us was the correlation between the casting process and the fatigue strength. For this, we used these kind of rules. We call it the Kainzinger and Grun rules that correlate the graphite nodule count to the fatigue limit. So we extrapolate from their work this curve, and we use that to map the fatigue strength all over the components based on what we simulate. And this is what we get. We performed the magma iron, and we exported the nodule count with the magma link to ANSYS, and then we mapped the safety factor, use this kind of, use the Grun-Kainzinger law. Just for all information, before doing that, we have done a project with the EV section ductile iron casting to see the correlation between the results on nodule count and the actual nodule count. And we got a good correlation, at least from the qualitative point of view. This is why we decided to go for these rules to check the strength of the component. So we performed this again, the structural optimization, or better, we took the results of the structural optimization and we compare not with an homogeneous strength, but with the strength, local strength. And we got really a bad news, because looking, comparing, sorry, the stress with the local strength, our safety factor went down from 1.3 to 1.02, meaning that just taking into account the fact that the strength is not homogeneous, we went from a feasible result to a result that was not feasible for us. It was too risky to go ahead. Second stop.
So if I start just to clarify the last point here, so if you assumed homogeneous material behavior, you would have a safety factor of 1.3.
Exactly.
But when you considered the local material variations, you could see that you were really at a factor of 1.02, right?
Yeah, because the optimization was driven by an homogeneous material. So that was, let me say, the mistake that we did. And so when you compare the stress analysis made using homogeneous material to the strength, local strength, then you go down from safety factor from 1.3 to 1.02. That was not acceptable at that time.
But this is quite interesting, because typically when you do optimization of parts, you assume that you have homogeneous material behavior, and then you do some kind of topology optimization or structural optimization. But really this, you think that you are being conservative by assuming homogeneous behavior, while in reality you are, you may be tricking yourself here.
That's true.
Yeah. Any questions from the audience before we proceed? I think you can continue.
Okay. So the first step was to introduce the casting simulation, meaning that in that case we started with the casting simulation, just one shot, and then we map the strength of the material on the machined part, and then this mapping was introduced in the structural optimization. So the optimization was always driven by the structural variables, but just at the end of the optimization, the output, or at the end of each loop, the output, the stress output was compared to the local strength, just to see if we were okay with the safety factor. Then, at the end of the optimization loop, we performed again a casting simulation with the new geometry that the optimization loop gave us. We map again the local properties and we perform a pair of verification. And if everything was okay, the optimization ended. It could happen that due to a big change on the geometry during the structural optimization, there was no correlation, no strong correlation. So we decided maybe to do another loop, but was just a manual loop. What is important so far is that now we just introduced the casting simulation. It was just one shot to map local the properties and to get the strengths that would drive the structural optimization. So as you can see here, we got an increase on the safety factor, meaning that we were able to jump to 1.02 to 1.5, but with a huge increase on mass from 5,000 kilos to 6,700 more or less kilos. And here you can see that the light blue is all the material added to the first design to reach the target that about the stress and the safety factor. So in that case, we were safe, but with a huge amount of material that didn't make happy our responsible, because this means that the cost increased, the cost of the components increased a lot. So, Jakob?
Yeah, so what you did here was to add the consideration of local material strength
Exactly.
as a first approach to do that.
Yeah.
That you wanted. So you can see that you're adding quite a lot of material to decrease the stresses, basically.
Yeah.
It doesn't mean that you have improved the material. You have added material, so you reduce stresses, basically. Yeah.
And yeah, exactly. There are in that case, there are two factors that are fighting together. The fact that if you increase the thickness, you decrease the stress, but at the same time, the material will be, let me say, worse and worse.
Exactly.
So it's a fighting approach. So the big difference between the first step and the second step is that in the first step, when we put local strength property, it was just at the end of the optimization, just to verify that everything was okay. Now in the step 2, we introduce the local properties at the beginning of the optimization. So the optimization, as I mentioned before, is driven by also by the local properties. But there is no how can I say, optimization of the casting process. It was just a standard casting process that we discussed with the founder at that time, and was just a standard.
So basically, what you're doing is the kind of traditional thing that you do when you see that things are breaking. You add more material, you make things thicker. Basically, that's the traditional approach, is fix something that breaks. That's what many people think that you should do. But as you see, you kind of, okay, you do save the safety factor, but you have also increased the weight significantly.
Yeah,
it would be interesting to see your next step here.
Yeah, and instead, so starting from this, we discussed it and we said, okay, we don't need to think thicker, but we need to think smarter. And this is why we get this kind of approach, what we call the coupled optimization loop, where we introduce also the optimization of the casting process. So here you can see that there is two optimization, the casting optimization and the structural optimization. They are half coupled because the variables of the casting process drive the casting optimization, while the variable of the structural process drive the structural optimization. If someone will be able in the future to put the two optimization together, this means that both the casting variables and casting output and the structural variable and structural output will drive together the optimization algorithm. In that case, we have two different algorithms of optimization that are put together in this area. So we start with the casting optimization. We will see later which kind of optimization. Then we map, as before, the local properties on the machined part, and then we start the structural optimization. At the end, of course, we perform again with this modified geometry, both casting simulation and stress. We map the result. We perform stress analysis. And in that case, we had an external, let me say, algorithm that drive the two optimization just to be sure that we reach an optimized component, meaning that both the two optimization, even if they are split, are more or less in the convergence state. Of course, if the convergence were not good, we performed another loop. But in that case, the loop is done manually. There is no the supervisor of the optimization algorithm that can manage and drive everything. This is why. Okay. We will go to this discussion a little bit later. Now I would like to introduce the casting simulation we perform. Of course, it's sand hand molding with sand component. We performed the solidification simulation with Magma 5, and we have these design variables. So the design variables in that case was just related to the casting process, because all the variables related to the geometry of the components are related to the structural optimization. So we could change the allowances that was on the bottom part. We could change the shape, the dimension of the round, the cylindrical chillers, and the dimension of the square chillers. And the output variables that are involved in the casting optimization are the chiller volumes that we want to reduce to the minimum, the porosities on the bottom area that was the most critical area for porosities. You can see this purple here, and we want to minimize the porosities. And of course, we want to optimize the nodule count, to maximize the nodule count in the area, the most stressed area, that are the one here in purple. This is quite interesting because in that case, we don't want to optimize the whole geometry of the whole process, but we were really focused on the area where the designer asked us to get the best material, because that area was the most stressed. Here, just for information, are represented the casting process optimization variable. So we could change the allowances of the bottom area. We could change the diameter of the cylindrical chillers and also their height. And we can change the dimension of the rectangular chillers. Here there is a summary on the request. So minimize the porosity on this purple area, maximize the nodule count on the purple area on the top, minimize the volume of the chillers, and of course minimize also the weight of the casting. And here are the results, and they are quite interesting. As I mentioned before, is not full coupled optimization, meaning that you can see we perform three iterations where we get convergence, because the difference between 1.3 and 1.34 and 1.3 in the safety factor was less than our target on the convergence of the simulation. And we get this kind of result. So we get 1.3 as we wanted, but the weight of the casting goes down to 4,700 kilos. So less than the one that we supposed at the beginning. So we save 300 kilos. And you remember, with 5,000 kilos, the safety factor was much less, was 1.02 compared to 1.3. Here in the picture on the side, you can see that starting from the uncoupled one, we just removed all these red material that was not useful for our result, and we had this light blue material. So the geometry changed quite a lot, and not in a way we supposed it should change. That was quite interesting. Here you can see a trend from 6,700 down to 4,700. And in our opinion, if someone will put the two optimization together, so meaning that there is no the iteration made by hand, but there is a supervisor of the optimization that rules both the two optimization, we think that since there is a descending trend, there should be more savings in the weight. I could not estimate how much, but I can tell you that for sure there should be more rooms to reduce the weight of the casting, having always the safety factor and all the structural output inside the requirement. So just jump to the conclusion. We demonstrated that the shape optimization in the ductile components require local variation to get included in the loop of the design. And this means exactly what Jacob mentioned before. It's quite important to involve from the beginning the foundry, because otherwise you can have a misleading results as we got, because we got 1.3 safety factor, but then when we introduce the foundry ability, then we know that it was not so safe. Of course, we can integrate. We demonstrated that a sort of optimization loop can be feasible, making both casting process and stress analysis, because also at the beginning we were not sure that this was feasible. For instance, we could arrive at the point that there was no convergence trying to connecting the casting optimization and the structural optimization, while we demonstrate with 3 iterations that it was feasible. And of course, we demonstrate that coupling the casting technology with the stress analysis just from the beginning, just from the study, can give us a better result in terms of safety factor, in terms of stress reduction, and in terms of cost reduction, because I can get lighter castings with respecting all the requirements for the structural analysis. That those were the 3 points I would like to highlight, and I would like also to thank you for the attention and starting a discussion about this topic.
Thank you very much, Giacomo, for this presentation. I think it's really interesting, and it kind of really motivates a lot of the work that we are doing, and it also shows that this is quite an important topic, and that it's actually possible to do this. I think maybe you can, I will just share my screen a bit, and we will introduce the next part here, which is the panel discussion.